Okay, great. So I guess format-wise, I'll kick it off and give a brief kind of introduction. Just give you a not a pitch session, but at least a little context of who we are at Zapata and then and what we do. Yudong will talk about some of the things we're going to present the field in the context of dichotomies that we've found in quantum computing, and kind of try to demystify some of the things that we hear. And sometimes in the field, we get caught into this kind of polarization, I think, that happens in politics, and it also happens in quantum computing nowadays. And sometimes it's the truth, oftentimes is in the middle, maybe to one side or the other, but closer to the center. And there's some balance in these things. And sometimes the dichotomies that we create in our minds are really kind of false. So we want to kind of present some of these to you and give you maybe a new way of thinking through this. And then, Yudong will present some of them, and then I will present some of the other ones towards the end, and then we can wrap up and then have some Q&A. Next slide. So who are Zapata? Zapata, we spun out of Alain Aspero-Gushik's lab. I worked with Alain previously on machine learning, classical machine learning with chemistry, and Yudong was a postdoc in his lab working on quantum algorithms. He'll give a brief introduction when he starts his section, maybe in a little more detail. But basically, we spun out of the lab to create software that will help us accelerate the quantum revolution. A lot of people are working on all kinds of hardware, but we thought that the algorithms and software needed a dedicated commercial organization to work on those problems, because there are some really difficult problems that are not just related to the hardware that we can talk about in a bit of detail. So through discovery, development, and deployment of quantum computing applications really is how we intend to do that. Next slide. And the way we set about doing this initially was to go out to industry, to Fortune 100 companies and government organizations, and really look at the problems that they wanted to solve that might have a NISQ, particularly near-term quantum means of possibly solving that within the near term. And near term, I'm not going to give you a time frame. It's not obviously 2 weeks from now commercially, or 5 years from now, maybe, or 10 years from now. I don't know what the number is. We don't know. But the point is that there are organizations out there who would like to be able to eventually apply NISQ quantum computers and eventually fault-tolerant quantum computers to some problems that they have in industry. So we went out and we looked at these, and we work with Fortune 100 companies to see what those problems are, to help them formulate the problems in a way that you can solve them, hopefully with a NISQ solution. And we turn those into quantum actual solutions, discovery applications that will actually run on these things. Initially on simulators, on near-term devices in a smaller scale, and hopefully finding out the numerics necessary to actually do these things in reality with real data and real situations and real simulations in real life. And by doing this, we realized that the tools were kind of pretty rote that were out there. So we ended up having to go out and create specific tools that will help us solve these problems reliably, scalably, et cetera. And that's really what our solutions have become. We're an enterprise software company that offers those solutions that we use to service our customer to others and other developers in the community, to be able to leverage all kinds of software constructs that are out there, but are disparate and fractionalized. And we'll talk about some of that as well. Next. So basically, we exist kind of in the center of this Venn diagram. We're helping connect, enterprise partners, software partners, and different software ecosystems like Qiskit, Cirq, all these different things, and are made sometimes by the hardware folks that you see on the bottom. They also have software constructs that exist in this ecosystem, and the research community, the people creating the algorithms, the people in universities and national labs, and in companies who are working on particularly NISQ algorithms, and we serve kind of that concentric circle or set of circles in the center by offering tools that will help connect these people and make them more productive. Next. So why are we here? things have become polarized just as they are in society right now. Geopolitically, internationally, they are, but also in quantum computing, they've become kind of this way. And you see comments like this: we need to develop a quantum programming model that abstracts away the hardware, just like classical computing. Well, maybe. You can put most quantum applications into three buckets: chemistry, optimization, and machine learning. There's a lot of black and white thinking out there, and these kind of blanket statements that people tend to make. And the reality is that things are a lot more nuanced. Quantum computers without error correction are absolutely useless. They'll never do anything. NISQ computers will never work. Absolutely not. Well, maybe not. So maybe truth is somewhere in the middle. Maybe some version of non-fault tolerant things can do something useful. And there's a lot of evidence that's starting to point in that direction as well. And the truth is, when you get caught up on these black and white premises, these dichotomies, it's either this or that. You get into these kind of weird arguments all over social media, and it happens in our own quantum community. And it becomes a bit divisive. And the reality is, scientifically, the answer is kind of in the middle. And if we look at classical computers and how they developed, a lot of these all or nothing statements ended up not pairing out to be the same. It wasn't all about CISC architecture, not RISC, or RISC and not CISC. Nobody will ever use RF anymore. Well, not really. We still have RF chips in our phones, and ASICs still run anti-lock brakes, and use a general purpose computer for that either. Thank God. So next. The truth is, the stuff we're doing in quantum computing, to get it all to work, it's not even just about quantum computing. It is, in some ways, we can say that, quantum computing isn't really an industry. It never will be. I like to say that, there is no such thing as the quantum computing software industry. It will be just like the GPU industry doesn't exist, unless you're NVIDIA, maybe. But there isn't the GPU software industry. Yeah, you write software and you may utilize GPUs, you may utilize CPUs. And in a real solution, at least for big enterprise things, you use both. And you may use some Slurm jobs on an HPC cluster, and you might use a quantum computer eventually. This is VQE, the first NISQ algorithm for chemistry, if you will, the first variational algorithm that came out of Alon's lab. And the truth is that that little pink cloud on the right is the piece that runs on a quantum computer. That's maybe 100 lines of code, something in that order, right? That's a circuit, that's an ansatz that runs, and that gets changed and the parameters change, but that's the piece that runs on the quantum computer. The rest of it is all the data prep and preparation of the state that you're going to run on that quantum computer, and then all the post-processing that happens after you make a measurement, rinse and repeat, right, in this variational loop. The truth is, the other out of 28 Docker containers, when we put this in our Orchestra solution, only one of those containers is the quantum piece. The rest of it's a lot of messy classical computing. So it's not about all the quantum computing, and it's not about classical. It's both. And we need both, and we will continue to need both. So people say, well, quantum computers are going to take off. No, that feature probably doesn't exist, if ever. It's not going to exist over the next decade or two, probably. So oversimplified statements like, oh yeah, quantum computers do this or do that, or the classical computers are good for this or do that, are really oversimplified. The meta situation to this is much more complicated, and we need to be nuanced in how we think about these things, especially if we actually want solutions that are going to help in science, in commercial applications, in things that we care about, in places that we think that quantum computers are eventually going to help us with in problems that affect humanity. Next. So we think that we will make progress here, even with the uncertainty that's out there. It's not an if then. I really have come to the belief, especially over the past few months with the progress we've made with certain milestones in software, in hardware, that this is a when, not an if. But the when is a variable. But while we're in this development stage, there are some tensions, hard choices, and false dichotomies that, yes, actually, by having these false dichotomies set up in the tension, yes, it's this or this, it can lead to a discussion. But the truth is probably somewhere in the middle and nuanced and very problem specific. And there's not going to be a yes or no answer at the end. There's going to be a lot of nuance. And so we think that these conversations are useful. We think they can probably be less divisive. Usually, you know, the answer is in the middle, but they can help push us forward and really find the true answers here. And really, it can help us hopefully embrace some of the uncertainty that's out there and get to what the engineering problems are in software, in hardware, in algorithm development, in theory, and in experimental work that will actually push us forward to having useful quantum computers more on the near term. That's our hope. And we're hoping that, you know, by looking at these dichotomies, we can elucidate some of the reality of what the real problems are in this conversation. Next. So here we go. I'll turn it over to you, Yudong.
All right. So I'll delve into some of the false dichotomies that strike some of the keywords that you may or may not have heard either in media articles or even in some of the more academic settings. But before getting to the discussion, I just want to sort of introduce my background a little bit. So my background is in computer science, and I started working on quantum computing around a time, I think it was 2011, 2012. So that was suitably, you could say, you know, in retrospect, one of the low points of the field, because, you know, the craze of the 90s had passed. You know, all the hypes about Shor's algorithm, Grover's algorithm, all the excitements of the 90s came along, and then after 10 years, the field had still been playing with, you know, quantum computers with 4 qubits, 5 qubits, very small, very academic experimental systems, and so that was a time when quantum computing was largely an academic discipline. That even as an academic discipline, you would consider that somewhat on a fringe, because it's sort of a mix of computer science and physics, and physicists naturally, you know, neither side really want to sort of learn the language of the other. So that really contributed to the field. So at that time, the field is gained somewhat of a sort of notoriety in that, you know, you do need to be able to understand both physics and computer science to even begin to understand some of the technical contents of quantum computing. So, you know, we talk a lot about interdisciplinary research these days. I think quantum information and quantum computing is suitably one of the fields that are at birth an interdisciplinary area. And what that really means is it's sort of like, you know, blind people trying to touch an elephant, because the elephant is somewhere in between the field. So you need a lot of discussions and a lot of discourse to really clarify, you know, what are the true potentials of this technology. So with that as a context, let me just delve into some of the false dichotomies. So in the lingos of some of the more popular media, and also, you know, in many of the academia, there's the separation between quantum computers that are not error corrected versus quantum computers that are fault tolerant, because qubits today are still noisy, and then they're still vulnerable to the error and noise that comes from the environment, which makes the computation finite, which means that one has to fit a finite number of, one has to fit an entire algorithm onto a finite amount of quantum resources, and that's the noisy intermediate scale quantum era that we're in. And there's also a sort of decades-long efforts in the community developing theories about how we might use error correcting techniques to fight against these noise and error. And when we get to enough number of physical qubits, and then when these physical qubits becomes high quality enough, at some point quantum computers will be able to consistently fight off noise, and the quantum computing can last indefinitely. So this is the fault tolerant quantum computing regime. Apparently the exciting results that that people probably know about first, since Shor's algorithm, right, where quantum computers will break the internet, the quantum computers will factor large numbers and therefore compromise RSA schemes. So these algorithms are typically involving very deep quantum circuits. So they typically require the quantum computer to not only have a lot of qubits, but also it requires that these qubits be able to implement a lot of quantum operations. So in order to do that, you have to be able to fight off the noise and error constantly. So that's part of the reason why people believe that in the near term, most of the algorithm paradigms where people believe there is a rigorous quantum speedup is probably not suitable for the NISQ era that we're in. But more recently, people have been shifting towards looking at the quantum device and think about what one can actually do with it. So this is a fundamentally different approach from the sort of Shor's algorithm, you might say, approach, where one sort of looks at what theoretically one could do with a quantum computer. So you can think of this approach as more of a top-down approach, where we first look at the computational problem, and then we define the algorithm, and then we populate the steps onto a quantum computer, and then see theoretically how many steps are needed. So you could say this is sort of a top-down approach. And then this is more recently we have seen another sort of trend in the community, which is more of a bottom-up approach, where here's a quantum chip. What can we make the most out of it? What can we make the most use out of it? And it's a circumstance that's very relevant for companies like us, groups like us, who are trying to develop and implement all kinds of quantum software and applications. And so these two approaches creates sort of two separate clusters. So you have the theoreticians and mathematicians who come up with, who till today still they're writing very beautiful papers that where they mathematically cross the T's and dot the I's, and you can prove rigorous results about the algorithm. But the algorithm probably requires a fault-tolerant quantum computer for practical instances. And then there are also, including the work that our company was based on, is the variational quantum eigensolver that Christopher showed a few slides ago. These are algorithms that are more tailored towards the hardware. It's a bottom-up approach where we say, here's a hardware that has some interesting quantum mechanical phenomena. How do we make the most out of that for solving useful problems? So this kind of clustering, like this sort of two separate approaches, naturally give rise to the sort of misconception that a quantum algorithm is either sort of in the NISQ category. So you can either only do it for these noisy near-term quantum computers, and those algorithms are typically rather heuristic. You won't be able to prove a mathematical theorem about it, but in practice, you could show that there is a potential for these algorithms to work, versus the other camp, where you have these beautifully theoretically guaranteed algorithm, except that those algorithms probably require a lot of quantum operations and won't be practical for near-term devices. So it's easy to create this sort of misconception that we can sort of group the quantum algorithm into either those that are singularly focused on for NISQ devices, or they can only be useful when fault tolerance is achieved. And to just sort of paint the mental picture, so if we think about the state of quantum computer as living on this two-dimensional world, where on one hand you care about the speed, so that's the runtime. In this case, the lower the better, and then in the other case you care about the quality of the qubits. Then it would seem that there's a specific set of algorithms that people think about for these near-term devices, these noisy qubits. You probably need to take a little bit longer. They probably take a bit longer to run compared with some of the other algorithms, but they also operate on qubit that have lower fidelity. So they also operate on more noisy qubits compared with the sort of quote-unquote fault-tolerant quantum computing algorithms, where they are bunched up in this corner where you have to wait until the quantum computers have high enough fidelity, the qubits are good enough so that you can gain enough quantum speed up. So it is as though we are somehow waiting for a breakthrough to suddenly jump from the world of noisy intermediate scale quantum device to the fault tolerant device, so that so that we can all of a sudden start playing with these class of algorithms in the literature. But what needs to be recognized is that the physical hardware improvement, and this is just like classical computing, physical hardware improvement is always a sort of continuous process. And one of the metric for gauging the quality of a quantum computer is the decoherence time. So it's essentially how long does it take before the qubit becomes completely ruined by the environment and becomes classical. So this is the so-called T1. And this decoherence time has improved by a millionfold over the past 20 years. And the 2 qubit gate error rate, so this is also an important metric for the quality of the operations that you perform on a quantum computer. And this error metric has also reduced by 2 orders of magnitude over the past 15 years. So instead of the sort of proverbial breakthrough that we're all waiting for to go from NISQ into fault tolerance, physical hardware improvement is in fact taking on a continuous process, taking on a continuous path. And in practice, we often just need a quantum computer that is good enough for the job. We don't need the perfect quantum computer that lasts forever. We just need a good enough quantum computer for a particular job in order to gain the quantum advantage, in order to demonstrate value. And so this is one of the recent discoveries that we uncovered, where we show that there is a class of algorithm that there's a broad class of algorithm that you can, or I would say there's a general way of translating a broad class of quantum algorithms into a form where you could continuously leverage this sort of this improvement, where so essentially we developed an algorithm that continuously benefits from incremental hardware improvements. So this should be updated. So we have already uploaded those to the archive, and so they're already published. So back to the picture. So we had the cartoon a couple slides ago where we have the NISQ regime and we have the fault tolerant regime, and this is essentially the same box, except that we put the concrete numerical axes on the plot. So here you have the NISQ regime where the runtime is high, and for a particular algorithm, for a particular task, you would take longer to accomplish the task than algorithms in the fault tolerant regime. What we have shown is that there is a way to go continuously from the NISQ regime to the fault tolerant regime as the device increases in terms of qubit fidelity, and also also other metrics, for example, the number of physical qubits. So this sort of changes the perception that for a given quantum algorithm, you have to somehow get to it's either cheap enough that you can run it on a near-term device, or it has to be a fault tolerant quantum device where you can implement such a deep circuit. And some of the other observations that we find is noise affects the speed up but does not affect the accuracy. So this is one of the sort of counterintuitive observations that we have found. Typically, we would think that noise would introduce additional bias and make an algorithm less accurate. But here in this case, in the case of the quantum amplitude estimation, so this is the particular task that we were going after. In this case, noise actually doesn't affect the accuracy. It just slows things down. But the error in modeling the noise does affect the accuracy. So it is not so much that we are afraid of having noise in our quantum computer. I think an equally important question is how well do we understand those noise, and what our work has shown is that while reducing noise is important, it is equally important to understand how do you model these noise quantitatively. And the second point can essentially be summarized as if you've never been late for a flight, you probably spend too much time at the airport. So essentially you want the quantum computer to be just noiseless enough for a given job. So in other words, this is a sort of substantiating the point that we don't need a perfect quantum device for quantum speed up. For a given level of quantum speed up, we have a way of spelling out exactly how noisy we want the quantum computer. So exactly the level of noise that the quantum computer needs to accomplish in order to yield a specific level of quantum speed up. We don't necessarily need to wait for there to be 10 nines of fidelity in order to start doing useful things. We can start doing useful things. For example, if for an application a 10-fold speed up is good enough, then maybe we can already start making progress in with between 5 and 6 nines in the fidelity. And so this can be fidelity can be improved either by physical hardware progress or quantum error correction. So I've spoken with several people in the field about whether they believe 2-qubit gate fidelity can be increased indefinitely, just like how people once believed that you can pack the number of transistors you can pack on a given chip can increase indefinitely. So I think there's a divided opinion about this still, but we have a diversity of tools that allow us to continuously make progress from a high quality physical qubits all the way into a regime where you deploy some kind of quantum error correction to even further improve the level of fidelity. So this essentially points out a trajectory where you can algorithmically take advantage of the continuous improvements of physical qubits all the way towards the fault-tolerant era. So this is sort of breaking the dichotomy of so NISQ versus fault-tolerant. There is actually no dichotomy. There is a path where you can go continuously from one regime to the other as time goes by, as the hardware improves further and further. So that's the first dichotomy I want to discuss. And the second one is regarding quantum versus classical, and this is perhaps a sort of misconception that is more common among people who are very interested in quantum computing, but probably haven't invested a lot of time learning about the details. So it's one of those. I think it's one of those conceptions that's nonetheless interesting to mention, that a problem. So it's tempting to adopt this sort of perception that a problem is either solved entirely classically or entirely on a quantum computer. But the reality is that a quantum computer is really good for a specific subset of tasks, a specific types of tasks where we have some very clear idea that they are mathematically hard, and many operations, for example, operations of computing simple arithmetics or doing spreadsheets or running this Zoom app, for example. Those operations are inherently computationally efficient on the classical computer. They are far more sensibly performed on classical computers. So this inevitably points to the idea that to actually solve application problems, we'll need to use a hybrid paradigm where we need to look at the computational pipeline, and we look at exactly which pieces are hard and in what way, and only for the parts of the problems that is hard in a way that is suitable for quantum computers to enhance, then it makes sense to try to replace these parts of the pipeline with their quantum counterparts. But most of the remaining pipeline is probably still going to be classical, where you have the transition, where you have the on-ramp of where you pre-process the problem into a form that is compatible with quantum computers, and then you post-process it so that you can blend the solution of a quantum computer into the classical piece. So there's a lot of software consideration for this, but the high level picture is that quantum computer is probably going to be assisting with specific tasks in the industry applications that we know to be computationally intense for very specific, you could say, mathematical reasons. One example of how this really plays out is in machine learning, where you can imagine a hybrid scheme where you plug in a quantum computer as a latent space sampler for a neural network. So GAN is a very common model in machine learning. I think many people who, if you're familiar with machine learning, you have either heard of it or you have played with it yourself probably. But the general idea is that you have a set of data, let's say a set of facial images, and the goal is to train a model, train a generator that generates new data point that is as similar to the training data as possible. So in the case of facial images, maybe you're trying to implement some kind of deep fake routine where you're trying to train a neural network to generate images that are as similar to the human images that you send the AI as possible. And the way you do that is by challenging the generator with a discriminator, where the discriminator will be trained to distinguish between the fake samples and the real data, and in doing so, you're sort of improving generator and discriminator at the same time. So how could the generator generate novel data points? So in order to do that, it needs a source of randomness. So it needs to be fed some noise, and then the generator essentially is a function that maps white noise into pictures of people, for example, in the example of facial images. So in the classical setting, the noise is usually fed as just a uniform distribution. So they're just fed as coin flips, fair coin flips. But you could also think of an alternative scheme where you have a quantum computer, or you have some alternative model. You have some alternative source of randomness that feeds into the generator, and then this source of randomness is another neural network which learns the last layer of the discriminator. So in other words, you can think of a way for the generator to cheat, so to speak, to accelerate its training. You allow the generator to somehow peek into the last layer of the discriminator, and that turned out to enhance the training of the generator. Now imagine replacing this part with a quantum counterpart. So restricted Boltzmann machine is one of the common methods in classical computing, especially in the 90s, where people use this for generating samples, especially generating discrete samples. And you can imagine replacing this part with a quantum counterpart, where the quantum computer allows you to model probability distributions that are very hard to generate classically. So you have essentially, what you have here essentially is a classical neural network with an enhanced source of randomness that comes from a quantum computer. So this is just sort of going back to the original sort of high level message of, what does it look like for a quantum computer to actually plug into an actual application, right? So we're not generating the deep fake images entirely from a quantum computer. The quantum computer doesn't generate any images, but the quantum computer provides the essential information which can later be mapped by a sophisticated classical system onto something of real world meaning. So this is a concrete way in which a quantum computer actually plugs into an application, and that essentially allows us to start trying these noisy intermediate scale devices in practical applications. So the slogan, so to summarize, what I mentioned in the past couple slides, essentially is to classically divide and quantumly conquer. So if you have a complicated problem, usually you would think about how you divide that up classically, and then chances are there's some pieces that are computationally challenging, and then you try to conquer that piece with quantum, and that naturally gives rise to a hybrid scheme. And yeah, the implementation. So the example that I showed in the previous slide is just a particular example of this general framework, where in order to plug in a quantum computer, you need an on ramp and off ramp, and while quantum computing is doing its work, probably there also needs to be very close interaction between the classical part and the quantum part. An example like this stretches across multiple disciplines, as we have discovered. So the example that I mentioned is in machine learning, because I suppose many of you will probably have experienced on some level, the generative models, the sort of deep fake, etc. So you know about these applications. But there are also these frameworks that we see in other areas like quantum simulation. So in chemistry, in chemical systems, typically when you're simulating, say, how a drug molecule binds to a target, you don't want to model the entire system quantum mechanically, because at the end of the day, probably only the part where the drug molecule touches the specific spot on the target is where the meaningful chemical reaction happens, is where the electron transfer really happens. You probably only want to model that specific little piece quantum mechanically, and then treat everything else classically. And there are many techniques that people have developed for doing this. And also there are use cases that we've developed for optimization. And then the machine learning use case is actually the one I mentioned in the previous slide. And this design pattern is not just for NISQ devices, even though this is a paradigm that allows us to start trying NISQ devices. This paradigm is here to stay. So even if we have a fault-tolerant quantum computer, we also have every reason to have the quantum computer only focus on the hard piece of the problem, while the remainder of the problem should still be solved on a classical computer. So hopefully that instills a mental image about what it actually looks like when a quantum computer is being used for practical applications. The third aspect, I wouldn't say this is necessarily a dichotomy. This is perhaps more of a trichotomy, where I think it's sort of intuitive. I think it's almost a human instinct to find simplifications in understanding when confronted with a complex subject. So I think it's very customary for us to put things into buckets, and because that simplifies our understanding. And then with applications of quantum computers, there's also a very convenient way in which one could think of, what can quantum computers be used for? And you can probably find elsewhere where people say quantum computers can be used for simulating physical systems, simulating chemical systems. And in the same way, a 737 model in the wind tunnel can simulate an actual 737, because they both obey similar kinds of physical laws. There are also claims that quantum computers can be used to accelerate certain kind of optimization problems like routing, traveling salesmen, scheduling problems, these very hard NP-complete problems. And also quantum computers can be used for enhancing quantum machine learning. And so it would seem that there are these separate classes of algorithms that people have been exploring, and then they become somewhat disparate sets of efforts. But as we look at different applications that people have worked on, the more and more we discover that the reality is more like this, where you have these three circles blend into each other. I won't go into too much details on what these are, but there are very concrete examples of how some of the optimization methods essentially rely on insights from quantum simulation, and some of the quantum simulation problems can be rephrased as an optimization problem. And the same thing goes for optimization versus machine learning. And I think, if you're familiar with machine learning, a lot of the model training that happens in machine learning essentially are optimization problems. And you can very well turn that around and use machine learning in turn for solving other optimization problems. So we also have concrete examples for that. And then there are also this newfound connection between quantum simulation and quantum machine learning through some of our work. which also ties to the example that I showed a few slides ago about the hybrid quantum classical neural network. So that's about the application of quantum computers. And the last one is really about the design strategy. So now we have this quantum device, and we know that the way we're going to use it is to somehow plug it into a massive classical pipeline, and then we figure out the way, the exact algorithm that will take advantage of the quantum device. Now, how do we make sure that we are getting the most out of the quantum computer, right? So we could adopt the somewhat the strategy that is somewhat you will take it for granted in the classical world, where you just write a piece of code and then just submit it to the quantum processing units, and then you wait for the results to come back. And this is pretty much, you know, the kind of experience that anyone who's learning classical programming should expect, because classical computers are such mature devices. And every time you write a code in C, you don't think about how the code is going to be compiled and which register on the CPU is actually going to store the variable that you just defined, and how all the operating system, grunt work happens under the hood, right? So in the classical world, because our devices are already so mature, we can afford the luxury of this abstraction, where all we have to do is to type in the code in some text editor, and then submit it and let it run, and then just wait for the results. But because quantum computing is at such an early era, we cannot afford such luxury if we want to really do something interesting, or do something maximally interesting on current quantum devices. So this motivates this contrast between the sort of black box abstraction approach that people if you program a classical computer, it will be, you probably take it for granted. But if you ever program, for example, a punch card machine, I never had that experience, fortunately, but I'm pretty sure if you ask people who are old enough to have used punch card machines, they will tell you the very pain of having to figure out exactly how many slots to allocate for specific tasks, whether we're allocating enough memory for representing the variables, whether we're allocating enough stack space for executing these functions. So all these low-level hardware considerations becomes important if you want to actually use the device. So quantum computer, in that sense, is similar to the way people are using sort of punch card machine in the early days, where we have to look at how the qubits are wired together, and which are the ones that are high quality, and what are the 2-qubit gates and single qubit gates that we can implement, what kind of tricks that we can deploy to make these gates run better, and all of that all of that are relevant. All of that details are relevant when it comes to actually squeezing the most out of a given quantum device. But on the other hand, there are also ways that allows a programmer to abstract away all of that. For example, if you use any of the common paradigms like Qiskit or Cirq, I'm pretty sure they have the machinery for you to just build a quantum circuit, submit it to a backend, and then just wait for the results to come back. It's just that at this particular early stage, to really do something interesting, we really need to peek under the hood. So it seems tempting to think, right? So this is in the black box abstraction mindset. It seems tempting to think that quantum hardware is just some machine somewhere in the world that you don't need to worry about, and quantum software is what you play with on your laptop, and these two can be considered separately, just like how we consider pretty much anything that we do on the classical computing devices. And but this is likely not going to be enough, just sort of to belabor this point. And what we believe that in the near term, to actually do something maximally useful on a quantum computer, the algorithm needs to fit the hardware like a glove. It needs to, so the programmer will necessarily would want to dive into the details of the hardware and then see what are the native gates, how the qubits are wired together, and what is the application problem at hand, and then combine these information and think about what is the best algorithm to design. So as an example, we have recently released a study. I think it's in March. So it uses Google's Sycamore processor. So if you know about the quantum supremacy experiment that Google announced last year, that's the processor that they used. So we looked very carefully at the supremacy device, and we think very hard about what can we do with it. So what we came up with is essentially a quantum simulation task, which is one of the hardest open problem in condensed matter physics, where people want to investigate, for example, the phenomenon of high temperature superconductivity and what goes into the phase transitions of different materials. So the precise problem that we looked at is Fermi-Hubbard, the Fermi-Hubbard model. So this is one of those sort of fundamental science fundamental models in condensed matter physics that underlies a lot of applications in, for example, simulating solids and simulating other materials. So we looked at how to solve this on a Sycamore device, and what we did is we looked very carefully at the device on the gates level and on the pulse level. And then we also looked at how the qubits are wired together. So this is so every cross corresponds to a qubit. And then we looked at how the qubits are wired together, and then we figure out how to map, how to encode the problem onto the layout of the qubits very carefully. So each one of those blue circles corresponds to an electron, and then each up and down represents a particular way the electron can be. So then we look at the actual problem we're trying to solve, and then what really happened was we looked at the physical system we're trying to simulate, and then we look at how the processor, the way the qubits are wired on the processor, can be natively used for simulating this physical system. And then based on that, we think about what are the how do we use the native gates that are available on the hardware to generate this variational ansatz, which is just a tunable quantum circuit for the purpose of the simulation. And then given this level of detail, we then take this and then go back to the problem level, to the application level, and discuss how these low-level features give rise to meaningful use of this device for this specific application. So it seems that the Sycamore device is natively good at generating quantum states that represent states of electrons that are otherwise very hard to generate on a classical computer, and we have very rigorous theory that motivates that. So this is the type of sort of leaky abstraction that we believe is the kind of design pattern that's needed for extracting the most out of a near-term quantum device. And this is very different from the sort of black box approach, where we can very well go say, here's a problem, let's just write some generic technique and then send it to a generic transpiler, send it to a generic compiler, and then it'll give us some kind of gnarly looking quantum circuits, and we'll try to run it on the device. So that probably will not give us anything meaningful. But if we actually do it carefully, we just may actually extract something. We just may make a lot of use out of the device. So this is a concrete example of how the design pattern for near-term quantum devices is very much opposite of the black box abstraction. I think we're quite far from the era of black box abstraction. Maybe someday when we have fault-tolerant quantum devices, where the programmer can largely feel secure that she doesn't need to worry about the low-level details of the hardware, maybe at that level, you could start programming quantum computers without caring about the underlying details of the hardware. But even then, still, being able to know about the details of the hardware will pay off greatly. Because typically commercial applications will want to squeeze every bit of juice out of a given computing device. So so those are the false dichotomies that I mentioned, and they're largely centered around the technical details of it. There's a lot to talk about, this for sure, and I see there's quite a long list of questions popping up already. So at this point, I will turn over to Christopher to talk about 3 more dichotomies that are actually real, and try to see if I can look at some of the questions here.
Sure. Yeah, and so there are actually things that are real dichotomies or real bifurcations that we find, particularly when we're out there in the real world with business applications, and I think that's also useful to talk about. So the next slide, talk about one of these from the user perspective. Okay, looking at quantum computers now, should we be an innovator or an early adopter, or should we just wait and be a fast follower? Well, this is a real choice. It's an actual choice that you're going to have to make. And yeah, there's a lot of risk in on both sides of this. If you understand that this technology, as Yudong is pointing to, requires some knowledge of what the actual devices are, and that's not going to go away anytime soon. And that you're not going to be able to abstract away. There are folks in our community who will, be out there saying that, oh, we're going to get every database developer out there, or anyone who's programmed Visual Basic before in their lives are going to be able to program a quantum computer. Well, they may be able to do some abstracted tasks that have been simplified or generalized. But the truth is that you're not going to be able to really fully take advantage of those things unless you have some capability. So getting involved early means that you're going to be developing this IP. A lot of this, as Yudong referred to it, requires a restating of a problem in a quantum way, something that's tractable quantumly. And so to do that, you're going to have to develop new IP. The IP of, okay, here's my pre-existing classical formulation of an NP hard, NP complete type of a problem. Okay, how do I put that in a form that's actually going to be tractable in a better way quantumly? That's not always obvious. We've had many examples where customers have come to us and said, "Hey, can you do this?" And immediately, actually, Yudong has a couple examples where he said, "No, you can't do that with a NISQ algorithm." And I said, "No, let's try harder. Come on, you're a genius. You can do this." And then 3 days later, literally, he comes in and says, "No, we can do PDE problems on a NISQ algorithm. Here's how it is." But it had to be completely reworked, and the problem had to be reworked. So if you think you're going to show up, wait, and be a fast follower, and just, okay, we got the quantum computer now, and everyone's developed everything, let's just apply my domain there and quantumize it. That's not going to happen. So building the capabilities now really helps you develop the expertise to really understand your domain and create valuable advantages versus competitors as far as actually reformulating these problems and getting the data in a way and the problem stated in a way that's going to actually allow you to really use these devices when they come up. It's not that you're just going to show up and oh, I'm going to have the algorithm ready. I'm just going to press the big red easy button and have it happen. It's not going to be like that. Hardware milestones. I wish I had a chart on this. I do sometimes in my presentations to show you how the milestones on the hardware are really compressing now. It's happening quicker and quicker and quicker. It used to be that every couple of years we may add a qubit or two. And up to a few years ago, there was, maybe 1 or 2 qubits total in a system. That's not true anymore. And we're doubling the quantum volume in a matter of months or maybe a year now. And the amount of jobs that we can do and the commercial capability of these things is really getting much better. These are systems as a data center entity are becoming more and more reliable. It's not just a bunch of experimental physicists in the back room with some masking tape and some code hangers trying to get a system working anymore. It's actually becoming really viable as something that's more and more dependable. And I think we've learned about this in the past couple of months in a bad way with COVID. Exponential, what does that mean? And when you double something, when you go to the n qubits, as far as doubling, your compute capacity by adding 1 qubit, that's really the equation we're looking for here. What does that really mean? Well, we've learned about it with COVID. Oh, I only have 2 cases in my city, my state, my neighborhood, whatever. No, I have 10,000 2 weeks later. That's kind of what we're dealing with here when we're dealing with an exponentially growing technology or an exponentially capable technology. That the catch up is really hard, and we found that with this horrible epidemic that we're facing here. The capability of what you need to do when you have 53 qubits is very different from 64 qubits. That's not just a few more bits. That's orders of magnitude different, right? And that means that what you have to do on the classical side also increases as far as state preparation and everything you have to do. It's a much bigger problem to even prepare, and you have to be even more efficient on your classical state preparations and problem preparations and all of that. So the idea that you're just going to show up at 53 qubits and be just as good when you're at 63 qubits, you may actually be way far behind your competitor and not be able to really catch up. And be able to get the talent to be able to do that as well, which we'll talk about as well. So, this is a real dichotomy. You kind of have to choose. You have to kind of choose to make the investment now or later. If it's me, obviously, the people who are in this community have kind of voted with their feet that they're going to be in the commercial development area and think that this is a when, not an if. And we've made the decision to make this our careers. But I think that if you're a user, you might want to start thinking about at least having some investment in this, because the fast follower thing, unlike with some technologies, may not even be an option. So next. So, and I did touch on this a little bit, but it's also about IP. Maybe we can just wait. This is a real dichotomy that's going to happen. I mean, we mentioned this is just some of the patents that we have filed. I think we're up to close to 40 in just the 2 years that we've been around as a company. Major patent families on major innovations on formulating problems for quantum computers in this NISQ era. And some of these are fundamental, doing PDEs on a NISQ quantum device, like, for example, something that we've applied for a patent for, and some of these have issued. Well, if you require on doing partial differential equations for your problem, well, maybe you're going to need a license. So this is another thing to think about is, the dichotomy of not investing now. What does that mean? And developing in your domain the IP that's necessary to actually use these things and have freedom to operate in these areas going forward. We're doing this. But big companies like IBM, Google, they've published some things have issued already. You can see, and we're just a little company and we're doing this much. And if you have a domain that's going to be disrupted potentially by this kind of quantum computing, you might want to start thinking about that. And even if you don't do it yourselves, you might want to partner with one of the companies that's working in this area to maybe even co-develop or jointly develop IP for your area of expertise, because this is another real dichotomy, the haves and the have-nots that is going to develop over the next few years probably. And then there's a land grab, and you don't have any land, you're going to be renting, and that's just going to be the way it is. Next. And then, I touched upon this as well a little bit for what does it take to make that investment? Well, part of it is going to be, and this is a huge part of it, do you have the workforce that can actually take advantage of this? And I don't mean just quantum developers. Some of that expertise is necessary, but people thinking about a problem or working with people at least who are experts, like Dr. Gao or other people in other organizations who have this expertise, and kind of linking the domain expertise of what needs to be solved with a quantum computer with the proper solutions. And as we've said, it's going to be a hybrid thing, using your classical data and arranging that data and pre-processing that data. You're going to need experts who know how to do that in a way that is tractable on a quantum computer. And that may be different from the way that we're doing it. Probably is different from the way that we're doing that with a classical computer, which is going to require different infrastructure, different things. It's going to require people. And you're going to have to start thinking about, if you want to use this, what your workforce development is going to be. Or if you're going to work with outside help, you kind of have to make a choice there, and that's going to depend on the industry a little bit, and your ability practically to attract the talent that you need. You might want to do some thinking. This is a real dichotomy. If you are a hamburger fast food company, right? You may have some optimization problems that really could make use of a quantum computer, but you have to ask yourself honestly, am I going to get an A++ quantum computing developer who's done a postdoc at Harvard like Yudong to come work for the Burger King or the McDonald's or whatever that company might be? Maybe not. But you might have a domain expert who knows your operations research problem really better than anyone in the world. And you may need to be thinking about working with a consultant or an outside company to develop the expertise to be able to take care of that. Because if your competitor does that and makes that step, they may be, as we've discussed, far ahead of you. So making this choice about, are you going to use the outside or are you going to develop your workforce is a serious question. And if you think you're really going to be disrupted by this technology, and you think you can attract that workforce, well, you better get moving right now, because this is, there are a limited number of people who have this capability. We're trying to do more. I'm on the QEDC steering committee, where there's a workforce development committee that's supported by NIST and the government. There's the OSTP is doing a lot to try and develop a workforce. We're trying to do things educationally to build it out. But in the meantime, it's kind of slim pickings out there. So you really have to do some real thinking about whether you're going to be able to develop your own workforce internally. And if you're a quantum chemistry company or a company that's a pharmaceutical company that's already hired quantum chemists, maybe you can do some retooling there. Maybe you already have some people. If you're a finance company, maybe you already have some quantitative scientists with physics degrees who actually, with a little bit of work and working with some outside folks, could develop into those people, or you have the ability to track those people into your domain. But do you DIY it or do you DIFY it? Have someone do it for you. We have customers who very much fall into the latter category. They have no pretensions that they're ever going to be able to hire, a quantum scientist who'd be proud of putting that logo on their chest. Therefore, they've made the decision to partner with us and do it outside and have the solution developed. And at the end of the day, they just want the solution. They really don't care at the end of the day whether it's a quantum computer or Flintstone style hamsters running around in cages in the back room that's doing the work, right? The fact that a quantum computer can do it, great, but they don't really care about those details. In that case, you might want to choose to partner it out and work with an organization that has that expertise. But there's a legitimate reason, and we talked about the IP reason, why you may not want to partner it out. You may want to, buy a platform or use the computing part of that, but you don't want to tell people what algorithm you're running in your financial trade program. You're a hedge fund, and you know how to trade things, and you don't want to give that expertise to someone else. That's a legitimate thing. So you might want to start thinking about that workforce development now, in that case. But realize that you're going to need both vertical domain expertise and a deep understanding of the quantum paradigm, as Yudong discussed. This is something you kind of have to make the twain meet. You really, to get the juice out of a near-term device, you're going to have to know how those kind of noisy, funky qubits are actually working, and where the problems are, and the differences between, say, a superconducting gate and an ion-based gate. There are different native gates that you can even do, and so your problem might be solved differently. And there are different times of decoherence and different gate speeds on those things, and that may affect your algorithm. So you do need some of that deep expertise, or you need to consult with somebody who has that deep expertise to really make this stuff work and make it sing in a practical application. And then next. And so really the answer is this concentric circle here. of, discovering your use cases, leveraging domain expertise that you have in your organization. You need to think about acquiring your talent, or also incorporating the outside talent, and also the infrastructure and tools that you're going to need. And you're going to need all three of these things at some level to be able to do a quantum application. You need all of this. And if you go to a quantum company, they may not have your domain expertise. You're going to have to work to really maybe even reformulate your problem in a way that works for a quantum computer. And that's going to take some time too. The infrastructure, the tools, the technologies may be quite different that you're going to have to use here. You may have to prep your data differently. You may need new classical grouping algorithms to even prepare states that are going to run in your problem area. And again, the acquisition of talent is going to be important, and you have to think about where you're going to get that. And you're going to have to think about all three of these concentric circles on this Venn diagram when you're creating a strategy for your domain, for your company, for your institute. Next. And then, okay, this is one that we have in every technology area, but it's particularly acute in quantum computing because we've talked about, the IP sensitivity and the sensitivity of data. Do we keep our secrets, or do we do open collaboration? There are some models. We're seeing that pharma, we're involved in some organizations that in pharmaceuticals actually have worked together in technologies before with classical computing technologies pre-competitively to get together, because some of the problems there are not worth one company owning the IP or freedom to operate in that one area. It's actually worth it for them to pool their R&D resources in an area like quantum or big data analytics or these kind of things, and then use pre-competitively, come up with the methodologies and the algorithms that are necessary to do things in general, and then add your own special sauce in your domain, in your area. So if you're an oncology pharma company, you're going to do different things with that, but you don't have to go create the fundamental drug binding algorithm or the special quantum machine learning algorithm to do screening of libraries necessarily. So that may be that's a model that the pharmaceutical industry has used pre-competitively in the past, and so this open collaboration thing may work good, very well in your industry, and it may be sufficient. There are other industries where you can't do that, other areas of government where you don't want to do that, and there are legitimate places where some kind of closed ecosystems are necessary, a necessary evil perhaps. But what is true about this is that we do need interoperability of tools and technology for this to grow. And we've seen this in classical computing. There was a time when all computers didn't run the same software, and you had all kinds of disparate things out there. And that's kind of where we are now. Fortunately, we've learned a lot from classical computing, and things like using common languages and using common constructs and using some of those things have developed, and the idea of using open source tools and the open source community as a means of developing a lot of things has been leveraged in our community already. We see a lot of open source Python toolkits by big companies out there that are being contributed to, and libraries that are being contributed to in an open way. Those things are out there. However, we are seeing that some people don't want to give up particular IP in particular areas of their domain to their competitors. So that is a tension that really does exist, and you have to make some decisions here. As industries, as users, and also as developers and people who are in this community, as to what approach you're going to take with creating your tools and how you're collaborating with other people. It is a real choice, and it's not easy. It's complex, and I think is a case by case decision. Next. So here is the example from pharma, where you see Amgen and Takeda joining together in this Quantum Leap project to improve some delivery mechanisms and whatnot. So, you know, this kind of pre-competitive collaboration can actually happen, can be successful. We've seen it. The Pistoia Alliance exists to do kind of pre-competitive things in this area. We're a member of that. Some others here are members. I believe FTQC, which who sponsor this as well, are also members in the area. So there are other competitive quantum companies actually collaborating in that context to create tools that are not yet ready to be competitive, and actually all boats rise in this kind of a situation. So this is a paradigm that has been successful, and I think can continue to be successful. Next. And so some conclusions and maybe questions in some way. I think dichotomies and stating things as dichotomies, yeah, it's nice to have controversy, and it sells newspapers, I guess, and blog posts, and it makes quantum Twitter really fun for us in the field. But you know, there's some use that comes out of these locking horns in a way discussions, because they do help us push deeper into our understanding of where the truth with a capital T really lies in these areas. And as we gain experience with quantum algorithms, programming, and the hardware, the subtleties that we draw out of these conversations become really significant, I think, is another point here. It's not a black and white world that we live in. And certainly in quantum, we deal with superpositions and entanglement and all this kind of thing. So I think that's maybe instructive as a metaphor a bit here. You know, so the truth is somewhere in the middle a lot of the time, and we need to be aware of that and the nuances. This is nuantical technology, and nobody has the answers yet. That's the truth. And I think we can say, you know, as an organization, Zapata, we are committed to staying at the forefront of these discussions. We're out there. You've seen us on quantum Twitter and some of these places, you know, diving deep into the mudslinging controversy of some of these dichotomies and whatever, because it's fun, but also because we think it drives the scientific discourse further. And as long as we remain hopefully civil and energetic and engaging with the community, I think it does help all boats rise to have these discussions. It's useful to have dichotomies and talk about things in dichotomies, because it helps, you know, draw things apart. But again, truth falls somewhere in the middle, and it's a gradient. Next, thank you. So I guess we can open up to some of the Q&A. Yudong, did you see anything come up here that we want to kind of answer live initially?
So I think there's a question asked about can we summarize what kind of problems are more suitable for quantum computing instead of classical computing? Yeah, well, we know the computational computation is intense, but the quantum computer is still immature yet. So I think this is a question that maybe we can answer live. And
yeah, I mean, you know, it's still immature right now. Right now, the answer is you can't do anything useful with a quantum computer that commercially today. Yeah, you know, today. Maybe it'll change tomorrow. Maybe someone in our field will be able to really make a breakthrough, or we'll have 100 working qubits with 9 nines of fidelity tomorrow. But that hasn't happened yet. So the truth is, you know, we had this very specialized supremacy experiment that Google completed, but it was a very random type of, it literally was random circuits that they were simulating. It wasn't something commercially useful, but it's going to happen at some point that we find something that breaks through. Today, that's not the thing. But I think, you know, Yudong did mention, you know, certain categories of problems where we feel that there may be some speed ups, some tractions, the GANs particularly, where there may be an advantage in using the way that quantum computers solve a problem that will have a commercial meaning in the nearer term. And when I say nearer term, that doesn't mean tomorrow, next week necessarily. That may be 3 years, 5 years, 7 years. In some ways, that doesn't matter really, because if it's within a decade and it's going to disrupt your business or give you a really big advantage, then an exponential advantage in solving these problems, then it's probably worth doing, as I described. It is immature still. But there are some things, some areas where at least the evidence is pointing to, even in these model systems, you know, if you plot the chart, that they're going to approach having some kind of advantage. The evidence points in the right direction. Although I can't say today, yes, this one is definitely going to beat a classical computer. And also keep in mind that it's a cat and mouse game, because every time, you know, you come up with a quantum algorithm that can do this, like a new version of QAOA that can solve this optimization problem better than a classical computer did, and here's some nice data, somebody who's working on classical algorithms who doesn't want to lose his job or her job is going to come up with a better classical algorithm that may defeat that. This really is a kind of cat and mouse game. So I don't think that there's a clear answer. Yudong, do you want to build on that?
I think right now we have some good intuitions as to where to look for problems that are hard classical, and also quantum may have a chance of outperforming classical computers. For example, the two examples I showed before, one is the quantum simulation, which is to simulate how electrons, how systems of electrons evolve. So this essentially underlies all things chemistry. If we want to understand how much energy is released when two atoms come together. These are the fundamental problems in, for example, drug discovery, in material simulation, in many of the areas that touches the basic aspects of chemistry. You would need to figure out, you know, how electrons interact. And in spite of decades of effort, this is something that classical computers still struggle at. And then quantum computers offer a path where you can both efficiently and accurately simulate these electron systems. So that's one place where we believe quantum computers could provide an advantage. And then the other place is along the line of the quantum supremacy experiment, which is in terms of generating samples. So because quantum states are objects that are hard to replicate classically, so there is a rigorous sense in which if I have access to quantum mechanics, I could there's a game I can set up where I can prove to you that I either have actual quantum mechanics resources, or I have, you know, superluminal communication ability, you know, which is absurd. So there are rigorous sense where people have shown how quantum states are objects that are fundamentally hard to replicate classically. And the idea is that you can use quantum states to generate probability distributions, or you can derive statistical power from being able to prepare these quantum states that otherwise, you know, classical computer would not be able to have. So the GAN example is one very direct way how this statistical power can play out, where you use quantum computer as a source of randomness, and then in principle the neural networks that you use is tapping into a resource that are otherwise fundamentally hard to replicate classically. So that is a second place where we believe quantum computers may achieve an advantage over classical computers, which is to build statistical models of data points, or to generate probability distributions that are otherwise very hard to generate or sample from classically.
And I have another question here from Ryan. Watched a panel recently in which a panelist stated that currently, in order to work on really interesting problems in quantum computing, one needs a PhD. Do you agree with this assessment? I'd say categorically no. To work on the area and work on the problems, we have some employees who don't have PhDs and are some of our more productive scientists and programmers. One person that we have doesn't even have a bachelor's degree, and we had actually a high school student who joined us for a year, came right out of high school, I should say, and before going to college, and worked and was very productive and was one of our best developers. So you don't need it for some work, I would say. If you want to get into, some of the noise models and, hardware-centric problems and the engineering problems there, it would be very helpful, let's say, to have a PhD and to have worked in that area and probably have a postdoc under your belt, to develop some of the theoretical capabilities of doing this. Unfortunately, there aren't a lot of applied master's degrees or applied bachelor's degrees in this area. You just have to kind of get lucky. It's kind of like the early days of computer science, where there was no computer science department. You went to an applied math department and you found a professor who happened to be working on computer science to do that. And that's kind of where we are today. So, a lot of times it is more likely that the people who have training in this area, have found interest in this area, and have found themselves working in this area, do have a PhD, especially if they're working really on hard theory and new development, new algorithms. They might actually have that background, but it doesn't. It's not a complete stop. It's just it's a likelihood function, actually. I believe. Yudong, do you have some comment on that?
Yeah, I would say a lot of the field hinges on being able to know, especially since I mentioned quantum computing fundamentally uses physics and computer science, so that makes for a particularly high entry barrier. So I would say for many, you would say quote unquote mainstream areas of quantum computing, like quantum algorithms, quantum error correction, and especially quantum hardware. So these, just because of the sheer amount of skill set that's required to work on these topics, I think it does make PhD program more advantageous than alternative routes. But there are exceptions. Just like anything, there are always exceptions. And we have people in the field who don't have PhDs. There, for example, Craig Gitney at Google. I think he's one of the better known example. I think he's done very good work related to quantum basic aspects of quantum algorithms, and you can read his papers, and they're every bit on par with, I would say, the leading experts in the field. But he I don't as far as I know, I don't think he went through a PhD program, for example. So there are people that do succeed, and it's just that those are probably more of the exceptions, and we also have an exceptional team members on our team, and they're able to do a lot of very interesting work. But I would say the quote unquote mainstream is probably to go through some academic program, maybe not necessarily PhD, but some form of academic program where there is some mechanism for one to learn with some guidance and with some feedback and with some advice. And fortunately, these programs are becoming more prevalent these days with the online classes. I think MIT is rolling out these online resources, and there are plenty of free resources on YouTube, and people, all the research institutions are posting their talks online. So I would say there are already plenty of resources that are just out there for people to take advantage of. It's just that the current state of things, which is probably just a historical legacy, where quantum computing has largely been an academic discipline. So the current state of things is that most people still come from that sort of conventional PhD trajectory. But I could see, in the future, more and more people coming from just like a hacker community, for example, someone who's just super enthusiastic and super insightful about particular subjects. And then they thrive as some of the top experts in the field.
And I think there are applied master's degrees starting to develop. I know the University of Wisconsin has one. The University of Rhode Island actually just announced that they're going to be opening up a program as well. I think intake starting next 2021. So these are happening, and I think that so there's no reason that you would have to have a research degree and do a research thesis to become useful here. But to Yudong's point, you're going to need some mathematical rigor to be able to do original work and to work, look at a domain problem in automotive or aerospace or something else and try to make sense of how originally you're going to apply that on a quantum computer if the algorithm doesn't already exist. Now, that's different from taking an existing algorithm and implementing it. That, I think, even I've gone to, IBM Q's, Grover algorithm and drawn the circuit and hit enter, I've taught, my high school kids to be able to do that. That's not hard, but to look at a problem and come up with an actual variational algorithm or a fault tolerant algorithm that's actually going to be a novel thing to do that, you're going to need mathematical rigor and probably some kind of computer science type of thinking, or at least formalization thinking to be able to do that. And there aren't that many really great shortcuts to do that. And then understanding the physics of the machines you're dealing with is part of this whole thing. So yeah, so I think applied degrees, applied masters, and that, like we have applied computer science degrees at the bachelor's level now, that will happen. But it may be a little bit more involved than just a computer science degree, because you're going to have to know some fundamental physics differences as well. So it'll be different, probably not the same. Maybe it's a master's degree for you to become really proficient in this area, I would guess.
Yeah.
We have another question here. Javier asks, quantum computing is an interesting technology to work currently. However, there are some limitations related to engineering. Could you mention some of these limitations? I guess limitations meaning what are some of the engineering problems that are still facing us? Error, obviously, we brought up here. And I think we can talk about different sources of error and how they're important, but fundamentally you have that, and then you have some algorithmic engineering problems as well. Yudong, do you want to comment on each of those?
Yeah. So the challenges fundamentally, I think it's on the hardware side, where you want to build qubits where the quantumness lasts as long as possible, and that's the sort of the T1 time. That's one of the metrics that people commonly use, which roughly says how long before the qubit decohere to a point where it is essentially a classical object. So you lose the uniquely quantum properties, and trying to combat T1 time essentially has to do with looking at the details of how a qubit is actually built. So in the case of superconducting qubits, we've been to some of the experimentalists' labs where they fabricate these chips, and in many cases to make the qubit last longer quantum mechanically, one needs to look at, for example, how the surfaces of the qubits, like the superconducting pieces, how the surfaces are treated, what are the material science that goes into the fabrication, the details of the fabrication. Sometimes a lack of purity. Sometimes if you have impurity in your superconductor loop, that can contribute to noises when you're actually operating the qubits. And it's all kinds of detailed materials engineering, process engineering problems. And then people are slowly chipping away at these problems. Sometimes they develop a new process of depositing material onto a substrate, and that gives rise to a resulting circuit that has lower impurity, or maybe there's a new process that removes some of the surface defects of these qubits, and those lead to a quality improvements in how long the quantumness lasts. And then, so this is on the level of how long the qubits last quantum mechanically if you just leave it alone. And then if you want to do things with qubits, if you want to perform operations with the qubits, then there are also the gate errors there are also a whole field which is dedicated to verifying, validating, and characterizing these quantum systems, which essentially amounts to, if I send a microwave pulse to a qubit, how do I know that the qubit is doing what I intend for it to do? So there's a whole set of detection systems that one has to set up and to make sure that there's the qubits are properly characterized. And a lot of times the noise is time dependent. So a qubit drifts from time to time. And we've seen real data from some of the benchmarks where if you look at the noise profile day by day, you can see that there's an underlying drifting that that is also somewhat challenging to take into account, but people are making progress in terms of addressing these issues. So when it comes to the hardware, it's a whole set of engineering issues to make sure to continuously improve on the lifetime of the qubit quantum mechanically, and also on the quality of the gate operations that one could perform. And also stack on top of that, there's the measurement error. So when you're done with the quantum circuit, you have to measure the qubits. And then when a qubit tells you 1, how do you know that the qubit is actually in the state 1? Maybe it's a measurement error. So you know, there's a finite possibility that there's measurement error. There's a finite probability that your qubits are maybe not initialized in the correct state. So there's also the state preparation error. And all of this have there's a big community of in academics and industry groups that are looking into these issues. So that's on the hardware side. And then if you gradually move up the stack, I think on every level you can see challenges related to extracting the maximum value out of quantum computers. So if you move up to the control layer, there's also the problem of how do you generate the optimal pulse sequence that controls these qubits, so that you can most efficiently accomplish a particular operation. How do you model the noise, and so that these noise models become meaningful for the purpose of developing algorithms. So these low-level hardware considerations will sort of propagate up the stack, and then as an algorithm designer, for us, it is absolutely critical for us to get into the details of the hardware, understanding the sources of noises, how are they characterized, what are the pulse control techniques, what are the details of the physical qubits, and then how the qubits are wired together. And then think about how we can, so given all of that physical setting, how can we build an algorithm that maximize the use of that? So in some sense, it's not only the challenges on the hardware side. These challenges also propagate up as we build the softwares, build the algorithms for the particular applications.
Can I add maybe one other that's a major challenge, I think, both on the hardware side and the software side, which is scalability. And on the hardware side, scalability, depending on your architecture, has different challenges depending on the engineering system that you're using. So with the superconducting qubits, you have a physical problem the way it's done now, at least with most of these vendors. You're bringing wires down physically from room temperature into this dilution refrigerator down to 10 millikelvin or something near absolute zero. And you need to do that to bring those pulses to the computer to make the operations work on the qubits to make these electromagnetic pulses work. But when you do that, you're bringing heat into the system, which is the whole purpose of having the dill fridge, this dilution refrigerator, is to get rid of the heat so you can get rid of error, get rid of the environmental noise to a certain extent. So you reach kind of this problem, this oxymoronic situation where you need to put more and more wires into the system, but that's creating more and more heat, which you want to get rid of, and that creates a real problem for scalability. And so there is a physical limitation that you come up against, and how many of these wires you can fit down, and how many qubits can you put. The chip itself can probably put 1,000 qubits on it, and you can fabricate and we've seen this with some vendors saying, oh yeah, I can make a 200 qubit chip. Yeah, you can make the chip, you can print the chip. The problem is actually getting these control wires down onto that thing in a way that you don't create more noise and make these absolutely useless 200 qubits. And then not avoiding crosstalk and all the other noise that we had when you start doing that. So that scalability issue is a problem, and that's for superconducting. You move to ions, they have a different scalability issue. It's how many, maybe it's 100 ions that you can get in a line on one of these traps that they have, but there's a limit to that. And then when you want to start increasing the number, maybe you have to have multiple traps or shuttle ions around between traps or whatever to entangle them across these things, and that creates its own problems. So each of these systems has different issues with the scalability. And then you move to the software side again, as you propagate up the stack, you still have a scalability issue in state preparation and these kind of things. If you're dealing with hundreds and hundreds of qubits and you need to create a quantum state for that, how can you do that in the time that you have? And how do you do that properly on a classical system? So, I think those are engineering challenges that will continue to be a problem as we move forward. People are working on these problems. They're working on the noise problems. We're seeing progress every day in these areas. So there's hope, but these are hard engineering problems that we're all working on in the field. And it's actually pretty impressive when you look at the progress that's already been made, in my opinion, on this. On all of these issues.
I noticed that there are two questions about what we discussed before about the skill sets needed to get into quantum computing. I think one is asked by Pedro Oliveira, who is in economics and would like to know more about how to get into quantum computing, where to start. And Carlos Nanzueta, who asked which mathematics subject would be the first to study when it comes to getting into quantum computing. So tying off the conversation we had before about hardware, I think if you're interested in knowing about hardware, there's a very different set of skills that's needed compared with if one just wants to know about quantum algorithms and be able to use quantum computers, be able to program using some of the existing programming tools like Qiskit to use quantum computer. So there's a big distinction, and I think most people here are probably more interested in actually being able to use quantum computers someday to solve problems. And if that is the case, I think if I had to name one branch of mathematics to study, I'd probably say linear algebra. I think this is one of those. This is one of those sort of least favorite class in college, but it's a backbone, it's a bread and butter of quantum computing. So I think some people would realize that in some sense quantum computing is all about linear algebra. If you know about eigenvalue decomposition, if you know about singular value decomposition, if you know about unitary transformations, if you know about vectors in complex spaces, right? So I think there's only a handful of very simple, a small set of specific tools in math that somehow gets repeatedly drawn on many areas in quantum computing. If you want to understand Grover's algorithm, then it comes down to the sort of the mathematics of two-dimensional vector spaces. And many other algorithms can be understood sort of from being equipped by similar mathematical tools. And I think a place to start, as far as a place to start is concerned, I started. So I was a mechanical engineer. So my undergrad background was neither physics nor computer science. So I was as far from quantum computing as anybody could imagine when I first wanted to study quantum computing. So for me, the entry point was Nielsen Tron, the textbook, and that really sets the foundation for getting into the field, for knowing about the basic building blocks. I know that there are also other textbooks that are published more recently. I haven't looked at those very closely, but I imagine they are probably more up to date as to the needs of recent quantum computing development. But from my own experience, Nielsen and Tron, the book called "The Quantum Computation and Quantum Information." So this still is a classic. So even if you don't plan to use it as the textbook or the book to read, I think it's still a classic book that is worth reviewing at some point if you consider quantum computing as a future career option.
Can I also add, for the economists, I don't know if this individual is thinking about going into actual computation, but there are people who want to go into the business side of this, or at least be involved in it. Maybe you're a marketing person, maybe you're a business developer or that kind of thing. There are still opportunities there, obviously, in quantum computing in this industry. A lot of marketing, business development still has to happen, and for that, the MIT program that Will Oliver and Isaac Chung and these people teach virtually, actually, has been actually really, I think, a great resource for some of the folks who we've worked with in the field and who've actually come from different areas, but with an interest in the area. It really gives you a fundamental viewpoint of a general idea of the hardware and the different architectures, and also some of the linear algebra, at least at a basic level, to really be able to understand it enough to at least be conversant in the field and to apply your own skills in this area, but understand what you're applying it to. And I would say people who want a survey course, that's also an excellent place to start and see if you like it. I think it's enough to get deep enough with real professors who are really in the field to get a general idea of what the problems are. And then maybe, make your decision as to, well, I'm really interested in the hardware aspects of this, or I'm really interested in the software aspects of this, or maybe nothing at all at the end of the day. But I think that's a really good course that some people that we know have taken advantage of. It's the MITx course, and it's, I think, 4 courses. It's nothing to shake a stick at either. I mean, this is pretty serious. I mean, it gets deep down in there, so you will have to do some math to get through it. That's unavoidable in this field. You're not going to be able to completely avoid it, I don't think. And then we did have a question also about B2B business. I think it was in the other forum, but I think it's worth touching upon. So in the B2B technology world, SaaS world, or I would imagine, how should we be thinking about quantum? Someone who works for Salesforce interested in the perspective of how the platform could be relevant for companies like this. Well, companies like Salesforce or companies that have data. I worked in an automotive company that had a bunch of data. Really, this is some of the things that you've seen here, GANs and some of the simulation optimization problems that we've touched upon have applications to data analytics. I mean, in some ways, a lot of this will become data analytics on classical data or quantum data with quantum elements to it, where we can get some speed up. Particularly, I mean, GANs are already used in analyzing the kind of data that's in a Salesforce type of a CRM database, for example. And machine learning is used in that area. So any place where you see machine learning and it's applied to database data, I think we may eventually, I think Yudong has touched upon this, find some quantum applications in those areas. So that's a place to start thinking about, what areas of that data are your customers using? They're analyzing their CRM data, or their data in HR or in supply chain management, or enterprise resources management and that kind of thing. We have customers who are actually working on those kinds of problems and those kind of data. And trying to apply quantum algorithms to get an advantage in those areas. So I think there's plenty of space to apply these technologies eventually in analytics, which I think at the end of the day is what B2B really comes down to. Did you have some opinion there?
Right. I think yeah. In general, it's it's a new sort of it's a new industry. So it's sort of like a startup. We're like a startup industry, right? So I think with with every sort of new industry, there comes the 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 sort of there's a new sort of ecosystem being formed by not just the domain expertise inside quantum computing. You know, in order to build quantum computers, I'm pretty sure there are all these surrounding industries that are also being influenced, like the consulting industries or some industry that have a non-trivial stake in the hardware technologies, like the companies selling dilution refrigerators or so I think, I guess, you know, my understanding of Salesforce is you know, it builds a software that keeps track of, you know, that is a tool for people to keep track of how these industries evolve, and I think it's just interesting to point out that we're also very curious to see how the industry landscape really evolves in the future. And it's not just the quantum computing science itself, but also there are consulting companies that are now having dedicated personnel doing looking to quantum computing. There are also all these industries that are previously unrelated to quantum computing starting to get connected. So those are some of the sort of macro scale changes that are also quite interesting.
And I think what are, oh, here's one. I think maybe Yudong, you should answer this because you're currently recruiting. What are the skills or abilities that Zapata Computing wants in a researcher?
So for
The last one.
yeah, the last one. Okay. Yeah, so our research, we want our research to remain very much at the forefront of you know, the current academic discourse, and I think that there's some areas that we specifically look at, which has to do with so if you look at our publication record, you know, we look a lot into these near-term quantum algorithms. But also we want to we want people who have a sort of unique perspective about quantum algorithms, about how you can use some new novel techniques for improving quantum algorithms that you can develop for near-term devices. So essentially, quantum algorithm experts, and also if you're a hacker, for example, if you're very familiar with the pros and cons of different quantum computing paradigms, those will also be very those will also be very useful team members, very useful, very interesting contributors. And because we're building Orchestra, which is our workflow engine for actually implementing the quantum solutions, we could also benefit a lot from even classical software engineers who are very excited about quantum and wanted to contribute very much on the classical side of how do we build the workflow systems, how do we make sure that the workflow can be implemented as efficient as possible on the cloud, on HPC resources. So the platform engineers. So those are also the skill sets that we very much look forward to recruit. And so in general, it's the science and also the sort of software engineering aspects that we look at very closely.
I think that's about the end of the time that we would have, and maybe we can wrap up. And first of all, I mean, from us, thank you for spending the time with us and some really great questions. Hopefully we've done a decent job answering some of these and giving you at least a general perspective of some of the issues that are in the field now. Thank you for the opportunity.